Monday.
Yeah.
What angle are they at? Oh, like this. So like this. Thank you. So let's talk about this. We know from X-ray crystallography, we know from observation that the angle between bonds in, say, methane is 109.5 degrees. It is tetrahedral. We also know that pi bonds are not tetrahedral. By the way, that name, tetrahedral, that describes that shape. That shape is a tetrahedron. Tetrahedron. So, yeah. Oh, I'm so sorry. There wasn't a message in that, I promise. But if there were a message, it would have been, no, there was no message. So if we look here, Sputnik. Yeah, that looks just like Sputnik. Okay, so let's look here. This is an s orbital, this is a p orbital, that's a d orbital, that's an f orbital. And none of them, bless you, none of them has a tetrahedral arrangement. Why are those the orbital shapes? They are. That's what we've determined. So these are the standard orbitals. So if L is 0, that's an s orbital, and it makes a sphere. If L is equal to 1, we said that's a p orbital, and those are dumbbell shaped. And remember, there's actually 3 of them, right? So we always said for the p orbital, 1 goes left and right, 1 goes up and down, and then 1 kind of goes backwards, forwards, right? The d orbital and then the f orbital, they get even more complex. They call the d a double dumbbell. And then f, they just give up. And what do they call its shape? Complex. It's complicated. So I like that even the textbooks eventually just go like, whatever. This doesn't work. So we know from lots of empirical evidence that s, p, d, and f orbitals have fixed shapes. And none of those shapes are what we find when things bond. Okay, they're radically different. When we have atoms in a free state, we see one shape of orbitals. And then as soon as they bond, we see totally different shapes. And this tells us that they must make new orbitals when they bond. Does that make sense? That's an empirical observation. The shapes don't work. So because the shape of the orbitals changes when they bond, we know that they must make new orbitals. Does that make sense? And this is where the idea of hybridization that we talked about yesterday actually comes from. So with that in mind, these shapes are very efficient for holding electrons and lone atoms. They do not, however, describe the shape of molecular compounds. P orbitals are at 90 degrees to one another, but when an atom makes 4 bonds to make a covalent compound, the bond angles are not 90 degrees. How long are they? Let's build one to find out. See, that's what we just did. Yeah. And what we end up with. What? Yeah. Come on. And so usually we'll draw something like this, where we show this kind of tetrahedral arrangement, where if these are on the same plane, this would be coming out of the page, and that would be descending back into the page. Does that make sense? And we call this shape a tetrahedron. And each angle in a tetrahedron is what again? Very good. Are you shocked? Okay. So hybrid orbitals are able to form in such a way that the distance between them is always maximized. So unlike regular orbitals, hybrid orbitals form to maximize the distance between them, which if you think about it, since this is now going to make this thing be stuck to another atom, when you start building big molecules, the basic arrangement is you want to make the other atoms in the molecule as far an angle away as possible so things don't collide and crowd into one another. Does that make basic sense? So hybrid orbitals always maximize the distance between them. And this happens because we say that valence shell electrons repel one another. That makes sense? In the valence shell, in the inner shells, those forces pushing the electrons in both ways, and they end up in these rigid shapes. But in the outer shell, there's nothing really pushing them in from beyond. There's no shell above it to hold them in a fixed shape. And so they're able to just repel one another as much as possible. And the result is the valence orbitals end up at the biggest possible angles to one another. We call this, well, again, the electrons in the valence shell repel one another. So this is called the valence shell electron pair repulsion theory. Makes sense, right? The electrons in the valence shell repel one another. It's the valence shell electron pair repulsion theory. That's VSEPR. And so, of course, we pronounce that Vesper, which you will note is not the way those letters are arranged. Clearly, it's Vesper, but we don't say Vesper because that sounds stupid. So we say Vesper, which I think sounds like a great name for a car company. What do you drive? I drive a Vesper.
What about like your child's first name? Like your firstborn child.
Like Vesper Orlando? I do have a child on the way. I might think about this.
That's such a cool name.
Here's the deal. He would be the only Vesper on his attendance, right?
Well,
Like, they'd never be like, Vesper, is that Vesper O or Vesper D? They'd be like, oh, it's Vesper D. Yeah, but right? Well, that's it. You'd hate to be like, your kid's name's Vesper. Every kid's name's Vesper, right? Like that'd be very disappointing.
You have the complication.
Okay. I thought I wanted to talk about this and I was wrong. So let's move on. So here's where we go. Remember, we said when the s orbital and all three of the p orbitals hybridize, we call that what kind of hybrid? Sp3, right? And in this case, ready? Sp3 hybrid orbitals are formed when one s orbital and three p orbitals are combined to create four new hybrid orbitals. These orbitals are not 90 degrees away from one another, but 109.5 degrees, which is the greatest possible angle between four spokes from a central point. This shape is called a tetrahedron. Tetrahedron. So if you look, and I've given you these very nice diagrams from the textbook, here's what happens. We take an s orbital and the three p orbitals, and we combine them to make new bonding orbitals. And if you look, they are really focused on one side, which makes sense because the other atom is over here. Does that make sense? The whole point of a bonding orbital is those electrons have to orbit not just your atom, but also that atom over there because we're sharing them. So they are really heavily weighted to one side, right? What do you do here if the other atom's over here, but the electrons have to go through all of this space in the orbital? That's not very efficient, right? So the hybrid orbitals are very distinctly one-sided. And that side represents where the atom they are bonding with will be. Now, sigma bonds occur in hybrid orbitals. What else always get found in hybrid orbitals? Lone pairs. So keep in mind, this is for any atom that only has sigma bonds and lone pairs. In other words, it's only sp3 hybridization if there's only sigma bonds and lone pairs. In other words, there can't be any pi bonds, no pi bonds, which means there can't be a double bond, there can't be a triple bond. Does that make sense? So when you're looking at your Lewis diagram, basically, how would we say? We'd say atoms that only make single bonds. Now, in this example, all 4 of those are being used to bond to another atom, right? You could think of this as like CH4, methane. That could be carbon in the middle, and each of these could be a hydrogen. Does that make sense? But it doesn't have to be, because we also said that any one of those could also be, it could be a sigma bond, but it could also be a lone pair of electrons. So if you look here, there's 4 possible shapes that come out of this. And that sounds complicated, but it's really not. It's really not. Just think about it. Look at this shape, and I've got it in 3D kind of space filling at the bottom. Now imagine, if all 4 of those hybrid orbitals make a bond, now we have something in the middle, and at 109.5 degrees, in that tetrahedron shape, we have 4 atoms, 4 bonds made. Well, this is a 3D shape. Specifically, it's a 3D shape called a tetrahedron. Have I said that word enough times yet? No. You're going to keep hearing it. And we said the angles are 109.5 degrees, right? But now I want you to imagine a case where 3 of the bonds are made to atoms, but one of the bonds isn't. One of those hybrid orbitals just has a lone pair of electrons in it. Well, now electrons are a lot smaller than atoms, so small that we don't really think of them as increasing the shape at all, right? So what we would have is the central atom and then 3 spokes down below. What shape is this? Well, a triangle's 2-dimensional. Is this a 2-dimensional shape? I want you to try it. Take your toothpick model, if you've got one in the right arrangement now, and take the top toothpick out, because there's only electrons there now. What do you have now? Very good. This is a pyramid. It's a pyramid. And again, this is still Sp3 hybridization. This is still Sp3 hybridization because those electrons are in a hybrid orbital. They're in an Sp3 orbital. Now, if we looked at water, by the way, water has a couple lone pairs of electrons as well. I want to make a note, by the way. What do you see happening to these angles as we go along? They get smaller. And they get smaller because lone pairs are really negative, and so they actually take up a little bit more space. So if you have a lone pair there, they crowd everything down just a little bit. Not a huge difference, but do you see how the more lone pairs we add, the slightly smaller the angles get? Lone pairs crowd other things out, and they make the angles smaller, such that the tetrahedron has the full 109.5 degrees, which is the maximum distance you can get. By the time we get to 1 lone pair of electrons, it cuts a couple degrees off. And now something like ammonia is down to 107 degrees. Now we get to water, and what would we say this shape is? This is a very scientific term. It kind of is teeter-totterish. I like that. Well, can I tell you what I was always taught? I'm sure there was a more formal one somewhere, but all I have ever heard, it's bent. It's not straight, it's bent.
I thought you were going to say bent. Is it bent?
No, it's bent. But note that the angle now is 104.5. Because again, the lone pairs crowd the angles down. And then if we have it's not that geometric. In fact, this can't be predicted. It has to be measured. So we know that anything that has no lone pairs of electrons, we always get the full 109.5. As soon as we add lone pairs, we just actually have to use technology to measure those angles. But we can predict. We can predict that they will be smaller. To get the exact measurement, you'd have to measure it. And I bet that they change under varying conditions, though I don't know that. I'm not an X-ray crystallography expert. I'm not an anything expert. Let's be clear about that. Question. That wouldn't be a complete octet, and so we wouldn't then be talking about a proper covalent bond. Is that a fair answer? Yeah. Electrons come in pairs. So when we're talking about stable things that actually exist in nature, the electrons are in pairs. And here you can see that now those lone pairs like crazy. What's the angle here? Well, there isn't one, because you can't have an angle between one line. I mean, I guess you could argue it's 180, but I guess. But I'm just going to say that the angle doesn't really apply. And we would just say that this is linear. So note, with Sp3 hybridization, there's lots of possible shapes. But, ready for a trick? Sp3, you get the 3D shapes. Does that make sense? Like, this is actually two-dimensional, right? This is flat. This would sit flat on a surface. This is two-dimensional. So these are 2D, but these are both 3D. And interestingly, you only get 3D shapes in Sp3 hybridization. That's a little memory trick for you. So if it's a tetrahedron, it's got to be Sp3 hybridized. If it's a pyramid, it's got to be Sp3 hybridized.
Does it have to be SP or can it be like 3D?
We will learn later on that you can have Sp3D 2 orbitals as well. You can start to throw d orbitals into the mix, but it always includes s's, it always includes p's.
Does it always have like 2 SP though? Or could it be like 3 SP?
Yeah, it could be in the 3rd shell, it could be in the 5th shell. You could have a 5 Sp3 orbital. That number in front just tells you which row in the periodic table we're talking about. That was a good question, by the way. A very good question. Okay, so remember, anytime you have no pi bonds, you don't need to keep any p orbitals, and it's Sp3 hybridization. So the quick check, all right, we're going to pick this back up on Tuesday and keep rolling with it, but the quick check to know what hybridization state something is just ask, how many pi bonds are there? All right, just look for double bonds, look for triple bonds, how many pi bonds? If there are no pi bonds, it's going to be Sp3 hybridized. All right, all of the p orbitals will get turned into hybrid orbitals. But sometimes we do need to make a pi bond. So recall that Sp2 hybridization occurs when one s and 2 p orbitals combine to form 3 new hybrid orbitals. All right, the orbitals are also not 90 degrees to each other. Now here's the question. What's the furthest away you can make 3 things from one another? Anyone want to try that?
120.
Good. In this case, it actually is 120 degrees. And if you look, when you do that, what do you notice about it? Put them in there at 120 degrees to each other. Yeah, I wanted you to measure it with a protractor. You cracked the code.
Well, yeah.
Congratulations. Yeah, good. So let's see. It's perfect. And if you note, that is perfectly flat. In fact, Sp2 hybridization is 2-dimensional.
Oh, that's a brass.
It's a brass.
Oh, that's the, I thought that was an A. Oh my God. Well, now I knew it was
Is it 2?
But like the first
I thought
time,
it was
I thought it was an A.
Definitely an expert at something.
There we go. Does anyone have any questions about that?
I didn't know we were learning German.
This is I.
What language is that?
This sentence eel in English.
Okay. Any questions?
Why you?
All right. So, so when we combine an s orbital and 2 p orbitals, now 1s, 2 p's altogether, how many orbitals are we going to get? 3, right? We take 3 orbitals, we make 3 orbitals. But now these are what we would call sp2 orbitals. And they are at 120 degrees to one another, which is much better than 90. And they're all on the same plane. They're two-dimensional. sp2, two-dimensional. Now again, this only happens if there's a double bond. And yet, look at the diagram from the textbook. What do you notice?
It's a figure of eight.
Well, it's 3D, but if you look, these are all on one plane. And they show that with the little kind of orbit around. So it is two-dimensional. We said this only happens if there's a double bond, and yet in their diagram there is no double bond. So let's add one. You're dead to me, textbook.
You lied to me.
There we go. So sp2 is when the central atom has one pi bond. There we go. Unambiguous. All right, and again, the reason it's now sp2 is that pi bond has to happen in a p orbital. So when it goes to hybridize, it can't use all three of the p orbitals. It has to leave one to make the pi bond. So now it can only use two of the p orbitals. And so an s orbital and two p orbitals, that's sp2. Okay. And now keep in mind, do these have to be atoms? I mean, obviously where the double bond is has to be an atom, but these could just be potentially lone pairs. So what are the possible shapes here? If all three are atoms, what will the shape be? We said it's two-dimensional, so it's going to sit flat. What basic shape does this give us if there's atoms in all three of those places? Yeah. In fact, the word we use is trigonal planar.
That is not a word. Why do you think that it's not a word?
Trigonal, which means like a triangle, and planar, meaning all on one plane. Trigonal planar. Frankly, if you say triangular, I'll give you the marks and then circle it and say, oh, I think you mean trigonal planar. And again, look at this diagram showing single bonds, but of course one of these has to be a double bond because this only happens if there's a pi bond. I'm very frustrated with this textbook for that reason.
One of them's white in comparison to the other one, so maybe that's representing.
I think it's a lighting effect, but maybe. Anyway, I'm going to draw the double bond in.
Oh wait, no, never mind. Oxygen gas does the double bond. Yeah, they're just.
So there we are. So that is trigonal planar, and that angle, 120 degrees, because in sp2, 120 degrees is the biggest distance between three things. Now, when we throw an electron in, what do electrons do? Lone pairs make the angles smaller because the electrons take up more space. They crowd everything else out. So this shape, like sulfur dioxide, first of all, what's this shape? You've seen it before.
It's bent.
It's bent. That's right.
It's bent, but it has a different.
But with a different angle. Good. The angle for this one is 119. It's a little bit smaller because lone pairs crowd out. And again, what do we hate about this diagram? Because it's got to have a double bond. It's not garbage. It knows something you don't, which is about something called resonance structures, but don't worry about it.
I'm sick of a lot. Tell us the truth.
Textbook doesn't actually know anything.
It depends on what you mean by knowing, which is an epistemological discussion that we're not going to have right now. And of course, we don't draw it here, but what must be here? Oh, that didn't. I had visions in my head of that being circular. Obviously, there's a lone pair of electrons here, right?
It's got eyeballs. It's evil.
But as soon as we look at this and see that it's making one double bond, that double bond tells me, oh, I have one pi orbital or one pi bond, which means it must have kept a p orbital, which tells me instantly, oh, this has got to be sp2. All right, you're going to learn. By the time we're done with this, you'll just look at that and just eyeball it instantly. You'll be like, oh, yeah, sp2 hybridization because it's making one pi bond. All right, and then here, of course, these have 2 electron pairs each. And again, this is just linear, just straight line. And angle doesn't really apply. Don't tell me what to do.
Still end up. Yeah.
Okay, I'm good. No, stop throwing things at me. Just okay.
Stop throwing if you catch it. Oh, what?
1 second, let me just kick my shoe off and I'll get it. Thank you. I will retrieve it and eat it at some point. Because I am not too proud for floor food. And you shouldn't be either.
I don't need this.
Okay.
It's in the wrapper. It's fine.
Okay, so we've talked about Sp3 hybridization. Sp3 hybridization happens when we have no pi bonds. Then we said if we have a pi bond, we have to keep one of those p orbitals. So now what kind of hybridization do we have? Sp2. Good. Now in the next case, how many pi bonds are we going to be making?
2.
2. And what are we going to call that hybrid state? Sp hybridization. Good. So
What are you going to stop for?
Sp hybridization occurs when we have a single s orbital and just one of the p orbitals. By the way, this would be like if we wrote the number, this is Sp1, and these are all,
Wait a minute.
they're one-dimensional.
How does that?
They can only be linear. There can't be any angle at all in them. And that's one-dimensional.
Yeah, I didn't know that was anything.
Sure, yeah. A straight line is a one-dimensional object.
I just looked at everything that was.
Right? If you follow that line along, it never changes direction. You never need a second dimension. You can, in other words, here's the thing. When we say dimensional, what's that mean? A line, you can describe everything you need to know about a line segment just with length. That's all you need to know to describe it. If you say it's 6 inches long, that's the only description you need. One dimension, one measurement describes it. That's what one-dimensional means. Now, when you talk about something you draw on a page, say a rectangle, now you need 2 dimensions to describe it. You have to say how wide it is and how long it is, right? So it takes 2 dimensions to describe that object. Left, right, up, down. When you talk about something that's 3-dimensional, now you need 3 measurements. How much left, right, how far up, down, and then how much out of the page down into the page, right? 3 dimensions. So when we talk about dimensional, it really means how many numbers does it take to describe this object.
Please keep going tonight.
Well, yeah,
Okay,
string
but
theory
then
gets all like
What
wacko.
about like the 4-dimension movie theaters when you're also moving?
So the 4th dimension in space-time is time.
Oh,
Yeah, so according to Einsteinian relativity, which I can only speak very vaguely about because just like I'm not anything else, I'm not a modern physicist, and I took one class in it once, but the basic idea is that we exist in space-time where for modern physics to work, we treat, basically, this is an oversimplification, but we treat anything in space-time as a 4-dimensional object. We can describe its x position, left, right, y position, z position, and then t position in time. Right? And you can describe anything that's ever existed in the universe in terms of those 4 values, right? Left, right, back, forward, up, down, position, and when in time.
One's length, one's
Yeah, I just
area,
figured
one's
everything that was
volume.
like flat was 4-dimensional.
Yeah, no, if something is flat and doesn't deviate in direction, it's now 1-dimensional.
So basically, the universe has
And a point is like, well, actually a point, like, and something that doesn't exist would be 0-dimensional. But
What about a circle? What kind of- so that's still a lot.
a circle is 2-dimensional because you would have to say, if it's a perfect circle, you would say that left to right it extends 4 centimeters, then top to bottom it would extend 4
But it's
centimeters.
all one line.
No, because there's all the inside of it as well, right? And it's a line that changes direction,
But it's
right? It still changes direction. Okay, so now with Sp hybridization, we will see this when the central atom is making how many pi bonds? Very good. If there's 2 pi bonds, now there's 2 ways to do that, by the way. That could be 2 double bonds, because each of the double bonds would have a sigma and a pi, but it could also be a triple bond. So this could be 2 doubles, or it could be a triple. Are there 2 p's in triple?
No.
But that looks awkward, right?
No, that's right.
That did look awkward to you? That looks like, I am thinking of Ripple, and as a result, triple is looking really strange to me, but I'm going to trust you. Why wouldn't I trust you? You guys are very trustworthy. Okay,
You did just leave the
Like,
class to
looking
another
at-
class.
exactly.
Looking at like the.
And as far as I know, nobody sent my wife hilarious texts from my phone. I have a good story about that, but I'm not going to tell it. What will the bond angle be here? What's it got to be? Very good. Bond angle's got to be 180 degrees, right? This makes a line. SP is one-dimensional. And again, man, do I hate this diagram, because it would either have to be that, or how else could I do it?
2 double double.
Yep, I could do it with a triple, or I could do it with 2 doubles.
I figured you wanted to make a line there.
Well, this is an interesting thing.
What? It's broken.
Oh, it's okay.
Maybe you've been trying to drive with the eraser this entire time.
Oh, when in doubt,
I'm using the wrong.
reset button. In this case, remove the battery and reinsert the battery.
But the
That's
battery's
what you
dead.
do when you're on a battery.
Listen, the best thing to do with any electronic device that doesn't work, and I wish I could explain this like to my mother, is just turn it off and turn it back on and call me if it's still not working. And like 99% of the time, Mom, have you turned it off? Well, what's that going to do? Mom, just turn it off and turn it back on.
What's the word?
What, plug
Get
it in?
mad and hit something and it starts working. Something maintenance. There's an actual like.
Oh, I've heard it. I'll think of it. Yeah, I've heard that too. Okay, so again, when we have a double bond, we will end up with a situation like this, like carbon dioxide, which has to be 180 degrees. And if it's a triple bond,
Still 100.
still 180 degrees. And if we have a lone pair of electrons, well, now angle doesn't really make sense, right?
We got these diagrams like this time.
Yeah, these ones are good. So those are the hybridization states. Does that make sense? We're going to do one question together. I'm going to leave you a few for homework. But I gave you a nice little chart that I find helpful. So here,
Oh, I thought that said spine, not SP.
here we have Sp2 hybrids. Oh, that 2 should be up top. This is the Sp hybrids, and these are the Sp3 hybrids, and it just shows you the possible shapes for each. And all of them can be linear, right? Like if they just have a bunch of lone pairs. But note, if it's 3D, it must be Sp3. If it's 2-dimensional, it must be Sp2. And they can all be 1-dimensional, right? You can always, well, I shouldn't say, sorry. If it's 2D, it's either Sp2 or it's the bent form of Sp3, right? That's another possibility. Okay, now with that in mind, let's actually look at an example. Let's talk about the carbonate ion, CO3 -2. So the first thing we're going to do, listen, the first thing we're going to do anytime we're talking about shape, hybridization, electron configuration, any of that jazz, the first thing we have to do is count, because we're going to draw the diagram. So I want you all to draw this diagram without me. All right, I'm going to walk around and say encouraging things like, good job. You suck isn't encouraging. You're doing better than Jack would be. Jack. I'm going to say Jack because there isn't a Jack in this room. You're all doing better than Jack. Jack has 0 in this course. His performance has been underwhelming. All right. You're all doing better than Jack. By the way, on your way out, I have your first quizzes here, Mark. So come get them on your way out. If anyone wants to take, I won't do this for other quizzes, but for this one, this is our first one of the year. If anyone wants a second crack at it, you can do so either today or Tuesday. Just come find me another time. So I just
Save that for the exam.
yeah, no. Actually, I had a Jack last time. He was awesome. I was great. And his twin sister, he was like 7'2". He was enormous.
I don't think that's that good.
No, but he was 6'8", which is not short. He was just a giant of a kid. He was like the most, and he was like the most hilariously like bumblingly awkward guy ever, but because he was so tall, he played on like every sport, right? He was just like, yeah, it's Jack, and Jack would like stand by the net and like.
Please tell me if you leave that down.
And how quick they hit, like, it's under.
Wow. The thing is, there's twins, and she was like just regular build stuff.
Wait, was she like the smallest person class?
No, she was just physically average, but he is just like.
Yeah, that's just.
They look great. I obviously I didn't actually like count the electrons to be sure, but on the face of it, they all look good. Yeah. Yeah, because all your BRs have 7, so they're maybe just 1 signal line. Yeah, that's perfect. Maybe it's full, so we don't consider it a valence. Yeah, perfect. P we did together, so that's good. Yeah. Whoa.
Sorry,
Whoa.
I just told Jack.
Yeah.
I made a mistake.
Oh, I like you put the hydrogen in there. Nice. Yeah, that's great.
Gosh.
How do you have these numbers? That is that one. That is that one. P orbital. Yeah, these look great. Really good. Did you do that at home?
Yeah.
Nice. Wow.
Watching the lesson.
You watched the lesson?
Yeah.
Were you able to follow it reasonably?
Yeah.
Nice.
But hold on. Really thanks. You don't think that really. Like,
No, it's just
talking.
me,
I was
right?
just like, it's so quiet.
I remember, like, for like chemistry last semester, I was like rewatching the lessons before the exam. And there was the one day when me and Kendra got called down to the office, and you were like talking about how it's because we're in a drug ring. And then we, and I left the room.
Please stop talking about
I left the room, and so I didn't hear it when I left the room, but I heard it when I was rewatching it, and you were like, I really hope she doesn't get arrested.
I'm gonna lose my job.
You cruded yourself.
Why would I regret that?
And then one of them came out. Never be your own lawyer.
No, it was a different day.
You were doing that a
There's
lot.
one where like people went to the office at the same time, like, oh, they're gonna have a fight to the death. And then one person came out for the other. Yeah.
I'm such a bad teacher. All right. How many? Please don't. I don't have any good moments, as it turns out. Fun fact. Okay, how many electrons for carbon? Oxygen? Yep, 6 times 3 for a total of 18. Ah, very good. Not fooled. We have a -2 charge, so that gives us 2 more. And our total is 24 electrons. Good, very good. How am I going to draw this thing?
Sorry, with carbon is the center.
That carbon's going to go in the middle.
And then O's all
Oxygen's all around. All right. They all get single bonds. We complete all the octets. It's not what?
It's not a pen sport.
It really isn't. All right, I've put 24 electrons on there. What do I have to do next? 24.
Make a double bond.
Well,
You gotta like.
There's 2 more electrons.
No, I put 24 on. So we're good.
You gotta like.
No, you have to complete carbons on.
I have to complete carbon's octet. So what do I do? Yeah, so what do I do? Yeah, and for the time being, does it matter which oxygen we pick?
No.
So I'm going to pick this one. Is that cool?
Yeah.
So I'm going to, and I don't like these ones up here, so I'm going to use those ones. And instead of having a lone pair, it's going to make a double bond. Cool. Now, let's talk about this central atom. Let's talk about carbon. What's it making? Or what's it got? Okay, 3 sigma bonds, 1 pi bond. Right away, what is your brain screaming at you? It's saying self. We know that this is in what hybridization state? sp2, because this pi bond means we have to save a p orbital, right? You have to save a p orbital to make a pi bond, which means when we go to hybridize, we have the s orbital, and how many p orbitals can we use? 2, because we have to save one. So this is going to be sp2. Hey, what are the bond? First of all, so the carbonate ion, 2-dimensional in shape or 3-dimensional? Does it lie flat, or will this be like pyramidal and all 3D in shape? It's going to be flat. What shape are we going to call this? Trigonal planar. Trigonal planar. Good. If you just say triangular, I'd be fine with that too, but trigonal planar. And so this will be trigonal planar, and what will its bond angle be?
120 degrees.
Very good. And it's going to have 120-degree bond angles. Will these be exactly 120, or would we expect them to be a little bit smaller? What do you think? What changes the angle from being perfect? What compresses them? Lone pairs. Does this carbon have any lone pairs?
Oh, yeah.
The carbon?
No.
So the carbon we would expect to have 120. By the way, we don't need to do this, but if I wanted to, if I felt so inclined, what's the hybridization state of this oxygen? Sp, sp2, sp3. sp3. What is the hybridization state of this oxygen? Very good. What's the hybridization state of this oxygen? Very good. How did you know that? Because that one's making a pi bond. Good. Does that make sense? All right. I want you to do the same for the next 2 questions there for Tuesday. That's not a lot of work. All right. I want you to listen. Shh. I want you to do that. I want you to make sure you have the previous day's homework done as well if you haven't. And I will tonight I am marking your kind of mini lab write-up things. They're super easy, just a handful of questions. Make sure you have them in. All right. There's no reason you shouldn't get like 9 or 10 out of 10 because they're nice, easy questions. But if you don't give it to me, I can't give you that.